I spent 10 years at Princeton. This is long ago. In my day. Every year there was talk of people saying, we're almost there by producing more energy than we put in, which would then make it an energy source for the world. They would say, oh, we're just 5 years away. And that was 30 years ago. So what's going on?
You're almost there.
Oh my God.
This is StarTalk. Neil deGrasse Tyson, your personal astrophysicist. I got with me Paul Mecurio. Paul.
What's up?
Co-hosting today.
Good to see you, my friend.
Good to see you, man.
It's always fun.
Love you. And you always doing interesting stuff.
I'm trying.
Yeah, you got your own like off-Broadway show?
Yeah, and then became Broadway, and then now we're taking it out around the country.
So I was going to ask you, when's it going to get on Broadway?
Well, we're coming back to it.
I'm tired of seeing you in the streets off-Broadway.
We ran into each other with 9 people across from the Late Show.
Off-Broadway.
They loved it, yeah. Yeah, called Permission to Speak, and it's directed by Frank Oz.
We love Frank Oz.
Yeah, he's the best. And it involves people telling stories and connecting people through shared stories.
So you're interacting with the audience?
Yes.
Yeah, cool.
Bringing them on stage, telling my own stories. We were just in Florida with it. We're going to be in Rhode Island. And people can go to paulmecurio.com to see where we're going to be.
Mecurio.
Mecurio.
Love you. Love it. So, you know what we got today? The day has to arrive in all of our lives when you want to be in arm's reach of a fusion expert. Fatima Ebrahimi. Did I pronounce that correctly? Fatima.
Almost.
Fatima Ebrahimi.
Yes, Fatima Ebrahimi.
Yeah, see, I got that, the last one.
Yeah.
Okay.
Yeah.
I love it. You have a PhD in plasma physics. That's a whole thing.
Yes.
Not just physics.
Yes.
Plasma.
Very specific.
You gotta say
Yes.
plasma. And you're a research scientist at the Princeton Plasma Physics Laboratory, PPPL,
Correct.
out there in Princeton, New Jersey.
Yes.
Up Route 1, I think.
Yes.
Yeah.
Mm-hmm.
You should come.
There's a fabulous Home Depot right there.
Yeah.
Big fan.
So this is, people have heard fusion, they've heard the word, and they've heard the word plasma, and most people think blood plasma.
Yes.
This is a completely different plasma, right? Blood plasma is like what's left over in your body.
Right.
I mean, after you take out the red blood cells, I
Right,
think.
exactly.
Yeah. So this is not that at all.
Right.
No, not that at
Let's
all.
start
Yes.
off, get the vocabulary on the table. What is a plasma?
So plasma is the fourth state of matter, and it's 99% of observable universe is plasma.
So it's really the first state of matter.
Exactly.
If you want to think of it that way.
Yes.
And it's
So
very
if you-
unstable, right? It's unstable.
No, not necessarily.
Don't
It could
disagree
be.
with me.
Just because you wrote notes doesn't mean you're correct, okay? Continue, Fatima.
It's actually, we are all floating in a plasma state in our universe. And if you want to see what is actually plasma is when, electrons are kind of freely moving and charged particles, negative charged particles, ions, positive charged particles. It's basically a soup of, charged particles, this plasma is.
All right, so why is it that we always, in physics, we see plasma joined together with the word fusion? Why are they relevant to each other?
Because our sun that actually produces a lot of energy is through fusion energy, and that's is in a plasma state.
So plasma, in order to get a plasma, it has to be very hot.
Yes.
Another thing is a cold plasma, is there?
Yes, actually, for the case of fusion, it has to be 100 million degrees to
100 million
actually
degrees.
achieve fusion. But plasmas, they could have variety of temperature. It could be low temperature plasmas.
Oh, but then you're not gonna have fusion.
Exactly. You don't have. Plasmas could also be lightning strikes. That's plasma. Yes.
So I remember this not a toy, this thing you could buy. Remember Spencer gifts?
Yeah.
Anyone older than 70 will remember Spencer.
Lava lamps.
Yeah, lava lamps. And all that.
Yeah,
Well, one of them was this ball. That it had this sort of glowing thing in it, and you put your hand on the ball, and it would react to your hand touching the surface.
Exactly, because it's charged particles, all of these,
Okay.
the plasma kind of
It makes the gas, it makes it glow.
Exactly, glow, because particles could also can de-excite and kind of produce photons and lights and things.
Okay,
yeah.
so the electrons recombine,
Exactly.
and every time they recombine, they give off light.
Exactly.
Right, okay.
Excite and recombine and de-excite, and you get the light.
So that's a plasma that's not at very high temperature.
Exactly.
Right, exactly.
Yes.
Okay. It was just
like
it
a
was
candle is also a plasma, but
Or the flame.
It's a flame.
The flame,
yes,
yeah.
the flame of a candle is
All right, so now you need high temperature for fusion.
Yes.
What are you fusing?
It's actually required for fusion. High temperature is required to fuse really light atoms, hydrogen, and also isotope of hydrogen, heavier hydrogen, deuterium, and a little bit heavier tritium, with having two actually neutrons. So they can collide and they can fuse, and it has to be really, really high temperature to be able to kind of overcome, these forces and create a lot of energy through neutrons.
So the forces are because you have a positively charged proton over here and another positively charged proton over here. Like charges repel.
Right.
Exactly.
They don't want to get together.
Right.
Yes.
And you're trying to overcome this with high temperature.
Yes.
Because high temperature means higher speeds within the soup.
And you're able to achieve the high temperatures, or we're still working toward the temperatures have to be high enough?
The temperature, actually, you can get very high temperature.
But are we there yet?
Yes.
That's what the protons ask on their long journeys. Are we there yet?
Are we there? I have to go to the bathroom. We're not pulling over.
Yes, we achieve really, actually, in the experiments or facilities that we have to create, high temperature plasmas to get to fusion. We really get to high temperatures. The temperature we actually achieve in a fusion experiments is even hotter, than the center of the sun.
Yeah, center says like 10 million degrees, something like that.
Yes, this is 100 million degrees.
What do you generate? What are you using?
They're trying to make another star.
Yes.
But what do you generate? How do you?
Don't
This isn't on, is it?
This kind of stuff that, like, when you were a little girl, were you doing these kinds of experiments in your basement? And then your parents said, "We got it." That's how the nemesis to superheroes are done. I'm going to make something hotter than the center of the sun.
Yeah.
We just got you an easy bake oven. Well, I'm going to turn it.
I gave it more power.
I gave it more power, and now it's 10 million degrees. You know what I'm baking? Plasma, and you're going to like it. You want it with or without mozzarella cheese?
Yes.
No, and then the lights of the town go dim. All right, so
that's Fatima again.
Yeah. You don't have to confess to that. That's fine. So how do you get high temperature?
Yes, how?
Because as I understand it, in order to make the plasma high temperature, something else has to be at a higher temperature than it. Is that right?
You get the high temperature because plasmas, carry electrons and current, electricity, current, you could say.
Because they can.
They can,
Yes.
exactly. They can. So therefore, they can get to very high speed and high temperature. So the question is that, so you get this soup, where it's going to go? So how do you confine it?
If it's 100 million degrees, what are you putting it in to contain it, to control it?
To control it is put a lot of energy through magnets.
Wait, so a magnetic field is
Yeah.
not a physical thing, so you
Yeah.
can't melt that.
Right.
Yes.
Right? And all your charged particles, they respond to magnetic field,
Therefore,
electromagnetism.
so it's
Right? And
it's another force that our universe is electromagnetic force, yes, that is long range. It's one of the fundamental forces, electromagnetic forces everywhere, our sun, all the stars, wherever you have plasma, you have electromagnetic forces, and they respond to it. So you have the gas, you need to make the state of plasma, which means that you can have some waves going into the gas, like antennas, and create your plasma. You could induce inductively current into your particles, plasmas. It can go around your chamber, which we are talking about a tokamak chamber, a donut-shaped chamber. So
A
Tokamak.
yeah.
Right, because Princeton has a tokamak.
Yes, it has a tokamak.
What
It's not a
what does that word even mean?
Yeah.
because it's Russian.
Oh, it's Russian.
It's
That's a Russian name?
It's
Oh.
two Russian scientists called this configuration
Toko and
tokamak.
Mac.
Yeah.
No.
They were a great act in the 70s in Atlantic City. They worked the Stardust.
Toko and Mac.
They worked the Flamingo.
Okay, so I did not know that. It's named for actual scientists. Very
So when
good.
you
No,
say
it's not
this
actual scientists. The two scientists actually called it. It's kind of their invention, tokamak.
So when you say this chamber,
yes,
the chamber is basically sort of harnessing or controlling the plasma.
That's the donut
Yes,
shape.
the
That's
donut shape,
that is
exactly.
being heated up at incredible temperatures.
Exactly. Various ways of heating the gas become plasma and heating the plasma to really, really high temperature.
But are we
Yes.
heating it to the point where we're at the cusp of being able to use nuclear fusion and get nuclear fusion that then propel
Yes,
rockets through space
yes.
much more quickly?
The rocket is a plasma propulsion.
Mm.
You actually get rid of the plasma you make from the back of the rocket. You're not confining it with magnetic field.
So the plasma rockets don't use fusion.
Not necessarily, they don't have to use fusion. But
Right.
if you know that in space, we don't have any power or there's no gas station. The only thing we have is our sun sitting there, and it's only going to give some amount of energy.
There are rest stops with McDonald's. though.
So if you want to go far, you need energy and you need fusion. If you're going to go stay around with solar panels, you have enough energy to
Locally.
use locally.
Yeah.
You could use that for just propulsion.
I remembered reading,
Yes.
because I know enough to know that in any gas, at any temperature,
Yes.
not all particles are moving at the same speed. Some are slow,
Yeah,
some are fast. The
yeah.
temperature is the average speed that everybody's moving. All right. I remembered that there's some method where you can pick off the fastest moving particles and put them over here, and their average temperature is going to be higher than where they came
Here
from.
we go. Treat them
Yeah.
special.
That's what it is.
Put them in the slower group.
No, they're
in
the
a-
fast class.
They're in a special class.
Leave everybody else behind.
Oh, my
and so
God.
you're cherry picking the fastest moving particles. Is that a thing? Am I remembering that correctly?
Conventionally, it's usually a collective, heating. It's basically you have through current, it's like current. Now, plasma also carry current. Current itself can heat,
Yeah, okay.
Really, it can actually, it's basically ohmic heating. That's one way of heating the plasma.
So that heats up internally.
Yes.
It's not hotter on the outside. You make it hot on the inside.
That's one way. That's a conventional way of
Yes.
actually heating up the plasma, the first way to do it.
Hey, StarTalk fans. I don't know if you know this, but the audio version of the podcast actually posts a week in advance of the video version. And you can get that in Spotify and Apple Podcast and most other podcast outlets that are out there. Multiple ways to ingest all that is cosmic on StarTalk. I spent 10 years at Princeton,
Yes.
and this is long ago.
Yeah.
Like, I'm old man now. In my day,
We didn't have electricity. We would just yell and someone would hear us.
so in my day at
Yeah.
Princeton,
Yes.
every year there was talk of people saying, we're almost there by producing more energy than we put in, which would then make it an energy source for the world, a very inexpensive
Yes.
energy source using readily available ingredients like hydrogen, which you will find at your neighborhood water molecule. They would say, oh, it's just 5 years away. And that was 30 years ago.
Yes.
So what's going on?
You're almost there.
Oh my God.
So wait, let's back up. So Princeton has a tokamak,
Yes.
but Lawrence Livermore has a different
Yes.
configuration.
So there are two approaches. One is just tokamak. Actually, fusion. Princeton has a special tokamak. It's called a spherical tokamak, which is kind of not like a donut. It's like a fat donut or cord apple.
How is that different than a standard tokamak?
The nice thing is that it's more compact.
Oh, okay.
So that's and other differences.
You
But
put
the
in your-
main thing
So
is
a really puffy donut.
Exactly,
Is a sphere.
puffy.
Yeah, okay.
You could say that a puffy donut.
Right,
Donut.
it was created by a fluffinator, I think, which was
I remember that. Oh my God.
fluffinator. Remember?
I think so.
So it's a tokamak, but a spherical tokamak,
Uh-huh.
and it's very special because of compactness and other things. And so by using magnetic field, you actually confine the plasma.
Okay, so there's that. So now let's go to Lawrence Livermore in Livermore, California.
It's so-called inertial confinement, means that by shooting lasers and at very small, dense target, you get fusion. So our plasma at PPPL, Princeton Plasma Physics Lab, is not that dense, but we have very high temperature. And so there's something we call a little bit specific, something called Lawson criteria, which is basically the multiplication of the confinement time, how hot you get, your density. So each
All of that combined.
combined, and if it's larger than something, you say that, oh, I achieved fusion. So inertial confinement has, more
Generates a denser. So
denser, exactly.
Of all of those factors, is density the most important thing that gets you to?
The sun gets high density for
Yes,
free
high
because you're in the
density.
center of the freaking
Yes,
sun.
yes,
It's
yes.
dense there.
Right.
So
Yeah.
so they get free density.
But what you're generating at PPL is not as dense. So
Yes, it's
sort of like it's what I would
confined,
get at Walmart versus
Yeah.
Saks. Like if I were buying a product, it would be like the lower end.
That's the first time those two stores have ever been in the same sentence. Ever. Wait, so you can have it dense but not hot, or hot but not dense.
Exactly.
And some combination of those two
Yeah.
will get you the fusion.
Yes.
Do we
and
know the
time
optimum
scale,
point?
Yeah.
Do you know the optimum relationship there?
So yes, we know the optimum is that you want to. First of all, fusion was achieved in around 1995.
But I have to correct that. Fusion was achieved like in 1947. It was just uncontrolled, and we called it a bomb.
Yeah.
Okay. Sure. At all times, she's referring to control fusion.
Exactly.
Okay. Pick up now. Pick up the story where you left off.
Where we're safe.
We got fusion.
We got it.
Yes.
It's everywhere.
We got fusion.
Correct. Exactly.
Okay, that's
right.
the H
exactly.
bomb. Uses the A bomb as a trigger for it. That's to give
Yes,
it
correct.
scale
Exactly.
of this. Yeah.
The controlled fusion was done at Princeton Plasma Physics Lab in the device called TFDR, test fusion reactor. It was obtained in
Achieved.
not achieved.
Yes.
It was we obtained fusion. It was achieved in the 90s here at Princeton Plasma Physics Lab, and also at another experiment jet in Europe later. So and about 10 million joule energy was or 10 megawatt million watt power was obtained. So we've got fusion. The
So
question is that
Just 1 joule per second is 1 watt.
yes,
Okay.
yes.
Okay,
So
so
10
she's thinking joules in energy,
Yeah.
but watts is a power. Okay.
Watt is the correct one. It's
Okay.
10 megawatt, and actually the record is 17 megawatt later. So it's around that much.
But I have a question. You have this big
Yeah.
fat donut,
Yes.
all right, and the whole thing is plasma.
Yeah.
But if you hit the fusion threshold,
Yeah.
does the whole thing undergo fusion? Because in Lawrence Livermore, they know if it's going to happen, it's going to happen in that little pocket
yeah.
that they created.
Yeah, it's basically in the vessel, in the core of the vessel. So it's kind of your plasma, it's in the core. It actually needs to finally touch the wall, and that's where you actually get the energy.
It's touching it's touching the magnetic field around.
Actually, there's a real wall. It's magnetic field all
made of-
around.
It's made of drywall, like plasterboard.
We call it blanket.
But what forms the blanket? In all seriousness, like what? What creates the wall? How does that work?
It's a various solution for wall. You know, it could be tungsten.
But does it come as a
It's
byproduct?
a various material.
It's a byproduct of the way you're manipulating the plasma. A wall creates out of that.
No.
Actually, no. You actually put a physical. It's a physical wall.
So why is it only measured when it touches the wall?
Because it's not measured. It's actually the plasma heat is being measured in the core.
Yes.
Yes, and that's when you get really hot plasma.
So what do you need the wall for?
Because it has to be confined, and the plasma needs to meet
But
some boundary.
But
yes.
we thought that was the magnetic field.
Right. Isn't that the magnetic field?
So the magnetic field is all around the torus, all around the donuts.
Okay.
So the magnetic
Oh,
field.
so the magnetic field gives it its shape.
Yes, exactly. Give it a shape. So you could say you could think that you could put direct magnets around your vessel, or you actually put coils that goes around your vessel, and then the wall, and then the plasma.
Have these magnetic fields. We've all played with iron filings and magnets, and you can see magnetic field lines, and they form these loops, these toroidal loops. Okay. I know that on the surface of the sun, because it doesn't rotate as a solid object, there are these magnetic fields in there that get stretched as the sun rotates its equator faster than other regions. And there are points where the magnetic fields snap. They break, and then they like reconnect. Does that happen in your space?
Yes, it happens on the surface of the sun, exactly the way you said. Sun actually, as you correctly mentioned, it's in a plasma state, also create, fusion energy. So a lot of energy in there. Another thing sun creates is magnetic field. All the motions of the plasma there creates magnetic field. So I'm creating magnetic fields. I need to get rid of this magnetic field somehow. These invisible field lines that I'm creating. Where does it go? It goes to the surface, and it kind of goes up like loops. And then the loops kind of, at some point, these invisible field lines, one go up, one go down, and then they snap. They kind of cancel each other.
Right.
And then we call it detachment. The whole loop kind of get away.
And it's chaotic, right? I mean, it's sort of, it's sort of like a bunch of, it's not controlled. It's like a bunch of 5-year-olds in kindergarten on Skittles. You can't control them. They're
on
loud.
Skittles. Oh, okay.
Okay. But it is, right?
Yes or no. It could be places that is really chaotic, but also it could be like a collective, ropes of magnetic field. They come together. They kind of cancel each other magnetic field, and then you get the reconnection site, and then the whole thing like detached. The plasma and the magnetic field. Yeah.
This is how you know that physics do this, not astronomers, because the people who study that are called magnetohydrodynamicists.
Oh my God.
That should not be a word.
No, that is one long business card.
With a fold out extra section.
Yeah, this is your business card. It's like that. It's
so let's get back to the energy, and then I want to go to rockets.
Yes.
So if you're going to be useful to anybody, you can't just make energy under the ground in Princeton, New Jersey. It's got to be, I don't want to call it portable, but it's got to be scalable. Yes. So you can move it to a town that can generate energy that has no radioactive byproducts. You can generate it 24/7, and you're just using hydrogen.
Yes.
Whose method will be better for this? The inertial confinement from Lawrence Livermore, or the tokamak design from Princeton and other places?
You have to pursue all the methods. It's
That's
actually
another.
I'm trying to say.
Oh, man.
Wow.
Man.
I didn't know I was in Congress right now.
That was what you say to members of Congress.
Yes.
Senator, we need to pursue all methods. Okay.
America is great. And I like pie.
And you even don't know about other methods. We call this some more innovative alternate method. But again, using magnetic field, to kind of confine plasma and get fusion energy. So all of them need to prepare, but all of them need to get to some condition. And the condition is that you get more, you produce more energy than you put in.
Otherwise, what's the point?
What's the point?
Right.
Exactly. It's kind
Right.
of the net gain that you kind of need to get. And we haven't got there engineering-wise. Physics-wise, scientifically, maybe in some range we can say that, oh, we got energy from fusion. And as I said, this happened also in the 90s, you know, at PPPL.
Yeah, there's a little bit of a overstatement about the Livermore experiment because that one had net extra energy from the experiment. And so it was championed. But the extra energy they got was relative to the energy that they put in this little spot. It didn't add up. The whole system that made the thing a thing to begin with. Right. So it wasn't the total energy budget of the experiment. It was just the energy budget of the
local
vessel.
around the target. Yeah.
On the
And
target.
it had to be
Yeah.
attached to that target or near that target to be an
Yeah, and that's how they make the measurements. So,
Yeah.
I think, correct me if I'm wrong, if you're going to scale that, presumably you get some good engineers in there to say, how do we make this littler and you can make this more efficient and then you just run the energy
You
out the other
actually need
side.
to also make better lasers, more efficient lasers, because the efficiency of it is not too great.
Right, because you have to put
yeah.
energy in the lasers to make the
Yeah,
energy.
because the lasers are going to help you to
you
get
need
the
engineers
fusion. Exactly.
the-
So engineering net gain is not too high in that experiment.
But the
And
physics gain
but
was
the
good.
physics gain was good. And also the physics gain is also for magnetic confinement. We have good gain before, and we are actually moving toward it with various, configuration.
Okay.
Yeah.
In all
Very
of
good.
this, the idea of excited particles and where does that fit into all of this, and sort of how do you calm down an excited particle? Jazz music? I don't know. Candles, scented candles. Like how do you?
You asking her how does she cool down the plasma? Is that what you're
in
asking?
a sense, right?
Because the whole
This
plasma is
concept-
excited particles.
Right, but there's specific things that you do to control the excited particles.
Oh, yes. I think that you just want the whole hot, plasma confined, controlled and self-heated, because it kind of interestingly, if it gets to some temperature, it can kind of on its own can get, heated the plasma for a long, long time and produce a lot of energy. And that is fusion system or reactor. And we have made a lot of progress in each, part of it.
But as usual, we're not there yet.
So how many years from now can I plug in my wall and the energy on the other side of that plug is fusion?
So, I mean, that.
She's going to say 5 years away. Then I told you.
Yeah.
Okay, we're listening. Go on.
You know that.
You didn't hear that. You didn't hear this. Go on.
I mean, that like diesel engines, are lots of, advancements.
Excuse me,
technological-
Senator, could I have the witness answer the question, please, directly?
She mentioned diesel engines. That is not on the table right now.
So it all takes decades, yes. And fusion it's a new physics frontiers, the whole plasma physics. When an experiment, is run, you kind of get into the new regime.
Because when you're doing actual research,
Yeah.
you're on a frontier.
Right.
Yeah.
You're not.
Well, I was just
you're
thinking
stepping
that.
where no one has stepped before.
Yes.
So you're going to discover new
So
things.
you're going to
Exactly.
discover, and you're going to discover hurdles that you could not have predicted. Seriously,
Yeah.
right? So
Yes,
in other words,
exactly.
so
Yeah.
I mean that's the issue, right?
Yes,
It's
you
like-
get into new regime, you discover new things, and in fact, actually, the whole rocket system, it was, a discovery through in a fusion system,
So let's pivot to that right
Yeah.
now, because it's still decades away before she's going to make my electricity. All right.
I mean,
Miss Easy Bake Oven over here cranking stuff up when she was 10, but she can't. All right.
but
commercially, viable. Commercially viable. I mean,
But everyone
we make
knows-
fusion in a laboratory. But
everyone knows how
commercially,
important that is
Yeah.
culturally.
Do we have
Yeah,
any
yeah.
practical application of fusion right now in any capacity that
Bombs.
other than bombs?
In a shorter time scale, we do not have to have a large scale fusion system to kind of give electricity to a whole city. We could have compact design for taking, for space.
Have you ever wanted one of your questions on the universe answered? We all have questions about the universe. From black holes to quasars, quantum entanglement, wormholes. There is no end to the depths of cosmic curiosity. Well, the entry level of Patreon membership with StarTalk gets you just that. I think it starts at $5 a month. You have access to the question line that reaches our Cosmic Query programming. And not only that, we produce a special Cosmic Queries installment just for Patreon members.
If you weren't the director of the Hayden Planetarium, what do you think you would be doing? What?
Okay, but this had to be another universe. It wouldn't happen in this universe.
Okay.
I'd be a songwriter for Broadway musicals.
Ooh!
So that's the entry level, and the perks ascend from there. There's a level, in fact, where we send you an autographed copy of one of my latest books. Right now, it's Starry Messenger, Cosmic Perspectives on Civilization. And it's signed with my fancy fountain pen with purple ink. So I invite you to just check the link below. And all of that money goes to our ability to experiment with new ways of bringing the universe down to Earth. So thank you for those who have already joined. And we welcome others to participate in this grand adventure of what it is to bring the universe down to Earth. As always, keep looking up. Right now, and forever, as long as we've had rockets, we've been using what we call chemical fuels, which means they're molecules that have energy contained within them, and you break apart the molecule, the energy escapes, and that is our energy source. And so that has not advanced in 100 years.
Because you scientists are lazy. You're not really trying.
We use different chemicals. We have solid rocket boosters. That's a different propulsion chemical than the big tank.
But essentially the same concept.
It's the same concept. Yeah. And so tell me about plasma rockets, because there's a lot written about it.
Yeah.
And we're not even talking about fusion yet. We're just keeping in your plasma universe.
Yes.
Tell me.
Plasma propulsion is basically we are talking about the next generation of rockets, specifically plasma rockets.
And they're highly efficient, yes?
Yes, they are highly efficient. In terms of, so there are several things about them, is that the exhaust velocity is really high.
What's hard for people to see, just being Earth surface dwellers, because you say, if I want to go forward, I just have to run or step on the gas. You're doing that at the expense of Earth beneath your feet. So the only reason why you can go forward is because you're putting friction between your foot on the Earth, and you're changing the rotation of the Earth slightly.
You're pushing back.
On it. You have something to push back on.
Right. So this is
in space.
You have nothing.
You got nothing to push back on. So the only way you can change your speed is to give something up.
And what are we giving up?
Mass. Take it from there.
Yes, you take it, and in this case, it's just you create the plasma or plasmoid through the process of like solar flares, magnetic reconnection, and you continuously detach these plasma from the back of the rocket and at high velocity.
Because it's at high temperature, and high temperature you get high speed.
Yes, high speed, and the rocket is being propelled forward. And it's not, it doesn't have to be high temperature. The interesting about the magnetic reconnection is that magnetic energy is being converted to kinetic energy. So it's all magnetic, yes? It's like the solar. It doesn't have to be.
So this is like, you want to get from point A to point B with this, you snap your fingers, you're there. It's like badass.
No.
Badass Google Maps.
Yeah. No, it's different because the particle comes out the back and the rocket recoils from it. But by how much? It's efficient, but what's the mass?
The mass is not too much. So there are various.
It's a tiny mass at high speed.
Yes,
and I have a high mass thing on the other side that can only then go forward at low speed.
Yes.
Right?
Yes.
So how am I going to get anywhere?
You're going to get anywhere by kind of having high thrust, high force. And that is through, again, exhaust velocity, you get it. And it's constantly, you're kind of pushing it, it's like a constant acceleration. You get somewhere in a space. It's different from,
Right. So you wouldn't use plasma rockets to launch.
No.
Because
This
they don't
is-
have that much, you can't send out that much mass. Because anytime
Yeah.
you see a rocket, this
Yeah.
is coming out.
So you've got to
Yeah.
This comes out and it goes the other way.
Use rocket
Yeah.
fuel to get it there.
To get it there.
And then-
Yeah.
And then through
So we're
empty
talking
space.
about like some in crazy. Is this sort of like a massive Wi-Fi spot that's like got incredible power? Is that what this plasma thing is? Where we're going with this?
Well, I think from what I've read, and but you're in the middle of it, so just
Yeah.
correct me if I'm wrong. When you're in free space, in open
Yes.
space, and then you turn on your plasma rocket, it's like one particle at a time, and so
Yeah.
you slowly accelerate.
Mm-hmm.
But acceleration is a constant, in this case, increase in your
There's also-
velocity.
Yeah, there's resistance coming on the rocket.
No, there's no resistance out there. It's a recoil, right? But since it's constant, and you do it for a long time,
For a long
you
time.
can reach very high speeds.
Exactly.
How fast can you go?
So based on the results that we have, and we are actually building a tabletop prototype at the
In your
Princeton
basement.
Plasma. No.
Tabletop.
Type that.
We're building this.
I'm using my oven.
Yeah.
At the lab, you're building it. You can get to 100, 500 kilometer per second. So it's still.
So that rocket can move at that speed. Could you have a
Yes,
sunroof on the
uh,
rocket at that speed, or would that be
A
viable? at all?
sunroof to see, just to.
You're just looking up.
Yeah, well, what is up?
Yeah, that's true.
No.
But you need to get to that speed, if you go to the moon, you don't need that much of a speed. And you could do it with this plasmoid rocket. You can do, small payloads in 3 weeks or something with this plasma rocket. And it's not that this is sci-fi. No, this is actually for real, because we do plasma propulsion with just electric field. Now we are doing magnetic, using electromagnetic field,
Okay, so-
using magnetic
Wait, but 3 weeks
reconnection.
is a long time. And astronauts, Apollo, they got there in 3 days.
Yeah.
But we're
So-
doing the fast, it's efficient.
Efficient.
It's efficient. It means that you go back and forth. It's not expensive. The fuel, it's flexible. You could use really hydrogen, the one that we want to use for fusion. Use really light atoms, so it's efficient. So it's fuel flexible and it's efficient.
Okay,
Yeah.
so you would use
it's
this.
like-
This would be
It's
the
like a nice car. Yes,
this would be the delivery vessel for
Yeah.
supplies,
exactly.
because you can just plan ahead, send it 3 weeks in advance, and then we get
Yeah.
there quickly. And supplies are very heavy,
Yeah.
all right, but you'll get there.
But wait,
Small-
we're using this plasma technology to get the supplies there. as
Well, I think the point is,
Yeah.
because you're just sending these very low mass particles, though they're traveling high speeds, the recoil is small but real and measurable, and it accumulates. So I bet if we were to fly humans with one of these rockets, it would only make sense if we were going to like Pluto or something, or to the nearest star.
Yeah, you need to use this plasmoid propulsion, you need nuclear energy, fusion, or some kind of a battery to kind of give you both force, the thrust, yet you need
But can you control it? So if you're approaching a planet's
Yeah.
atmosphere, can you control?
Yes, because
Otherwise, are you just driving that rocket right through the center of
Well,
that?
that's a big problem in space travel,
Yeah.
because if you can accelerate and you want to land somewhere,
you
you
can't
have
just
to
pull up like a
right.
parking
Right.
brake.
There's no.
All
Right. So what you have to do is flip the ship around and then have it send out particles the other way. So then it's a negative acceleration,
Right.
a deceleration,
Right.
and so that eats up some of your plan.
Yeah.
But might we use this going to Mars? Do you think?
Yes, because of it's because of efficiency. You could use chemical rockets
In
to
10
go-
years.
to go there once if you use all the resources you have. But you really need plasma propulsion for getting to the Mars. You also need the energy for that, and that's what the compact fusion compact system come. That's why we work on that.
Okay,
Yeah.
so the plasma rocket is not the same thing as a plasma fusion rocket, because the fusion is just a whole other source of energy.
Yeah, so the plasma rocket, the energy can come from just some solar panels. Because, for example, for the moon, we have the sun sitting there, so we can get, use the solar panels
But that can't
to
be
get the power.
But that can't be the level of compared to plasma fusion. Getting through solar panels cannot give you the same level of energy.
It's enough from the lower.
I want more than enough. I want the best. I'm an American, and that's how we do this in America.
But we don't even have that. We are not. This is like a FedEx going to moon and coming back. Yes, that's what we are talking about very efficiently. And you don't need that much of a power to do that. Like 500 kilowatt is enough. It's enough. You don't need millions
Right.
of.
So they get there faster,
Yeah.
but the guy still leaves the package like 20 feet from your door, and you have to walk out in your
And the
underwear
porch
to get it.
pirates steal it. Right, no.
Nothing changes with you scientists. You don't really advance
you walk out
us.
in your underwear to get your packages.
Yeah.
Okay, I will port you
My
next
neighbors
time.
requested that.
Yes.
Wait, so I just want to settle my understanding on this.
Yes.
When you have a plasma, you have high moving particles. You can send them out the back, and you recoil.
Yeah.
And the acceleration is slow, but it's steady, and it accumulates.
Yes.
Okay. So if you have solar panels, the solar panel is not itself a propulsion mechanism, but it's a source of energy.
Yes.
And you can channel that energy back into your plasma
Yes.
and keep the plasma going
Yes.
as long as we're close enough to the sun.
Exactly.
Okay. Now you're really far from the sun. You still need an energy source. And what would that energy source be if you can't use solar panels anymore because the sun is too dim? Would that be the
energy
fusion?
source, yes. It's fusion. It has to be non-chemical.
Yes, and non-chemical. So
It has to
so
be
your
non-chemical.
fusion source of energy would still be heating the plasma.
Yes,
It's
the
still a
fusion,
plasma rocket.
basically, yes. The fusion.
I had not appreciated that. It's
Yeah.
still a plasma rocket.
Exactly. It's still a plasma rocket because your magnets, first of all, you can use several, but you still have to power your rocket. And the source of power, it could be solar panel, or it could be non-chemical fusion energy. This is
Plus,
one
there's
thing.
plenty of hydrogen gas in the universe.
Yes,
So you can just scoop it up, put it in. So there are filling stations in the universe.
Yeah.
Told you that.
Yeah.
When it's going through space, is the plasma sort of morphing and changing, and do you have to account for that? I mean, because it can survive. My understanding is it can survive plasma in various states, right? I would imagine you have not been able to document every state that it can survive in, right? It's an ever-evolving science.
So it's just that basically you need the fuel here is like hydrogen, helium. Yes,
Right.
you have the fuel. You can actually use the local resources in a space for the fuel. So
And
that's
NASA
one
calls
of
it ISRU,
yeah.
In Situ Resource Utilization,
Ah,
which is a terrible acronym.
Yeah.
But ISRU, that's the big thing.
Yes.
Because then you don't have to haul everything with you.
Exactly. So that you want to be. That's why we call it efficient. Basically, it's fuel flexibility
It's
that you can
self-contained in a
kind
way.
of
It's-
and it doesn't have to be helium. It could be hydrogen, any kind, and it doesn't have to be argon because some of the electric propulsion, your gas needs to
argon!
be
Don't even get me
heavy.
started with argon. That's a ridiculous waste of time.
But why argon? Why not krypton? Or
all of them. It could be any kind of
I told her
gas
she was
that
a
you can.
superhero.
I was going
Yeah.
to
She's
say.
gonna use krypton.
I was going to say.
I told you.
I
got
feel
her
like
to admit
I've I'm weak around here. I feel. So
Yeah.
So there's you it can't exist on its own. It needs some other source of energy.
But what can't exist?
the
No,
plasma?
the plasma. Then you kind of you draw some. You create it. You ionize it. You create the plasma. Yes. So that's the specific. You have to read the paper and the patent to actually see. You see how the plasma is created from this fuel. local fuel. And then you get the plasma. But as soon as you create the plasma, you get rid of it from the back of your rocket
Right.
by
'cause you
the
have to-
process of magnetic reconnection.
And you've got to lose some of your mass.
Right.
Every
Yes,
time you go and
exactly.
going to go anywhere.
But that's what I was saying earlier. Magnetic reconnection is it's plasmoids get created. They're not very unstable, but then become over time unstable and decay. Magnetic reconnection sort of there's this constant instability in how you control that. And are you still working on being able to control that?
So for rockets, for plasma propulsion, we are not confining anything. So we don't care about stability, because in a fusion device, you confine plasma, you don't want it to go unstable. For a rocket, you just make the plasma, you use the magnetic field.
And then you just pollute space.
Yes.
I get it.
Exactly.
There you go.
Exactly.
You're not-
You get rid of it, and then you make new plasma and get rid of it, and then the rocket just gradually goes
Yeah,
the
and that's why you
direction
need
want to go.
1-800 gut junk for space, because you're just putting garbage into space. With that attitude, I understand.
But the plasma is not really junk, because, as I said, 99% of our observable universe is plasma. It's basically some charged particles you have in space that you always have low density plasma everywhere in space.
See, she was good. She said the observable universe.
There you go.
Because we don't see the dark matter.
Yeah,
We don't know what the hell that is, but it's not plasma.
yeah,
So she got that.
yeah. Yes,
got
yeah. So
this.
you could say that is.
Why aren't you
yeah.
altering with this plasma coming out of the back of a rocket?
Yeah.
Aren't you altering space in a way by putting these particles into space?
If space is 99% plasma to begin with, it's just
It's like
Not-
putting
it
more
doesn't
water in
care.
a pool. It's like putting more water in a pool.
yeah, it doesn't care.
It's like putting more
Doesn't
hair
care.
gel in my hair.
As I
Fifth state of matter.
Yeah, we are floating in plasma in the
Right.
universe anyway. So you kind of make some little plasma and get rid of it.
Yeah,
Go
yeah.
somewhere.
Universe won't mind.
Yeah, universe won't mind. Yes.
So Fatima, I got to land this plane.
Yes.
So let's. I want straight answers. You're in
Yeah.
Congress now, Professor Ebrahimi. How soon are we from having plasma energy generating centers in every city?
We are close, actually.
Can you give us
It's
a number?
5, but
5 years?
I would say 5 to 10 years.
Okay,
yes.
January
There are experiments.
2030. You're going to be right there.
We got our
So
number.
So in terms of that, but that is
We'll
then,
drag you back in here.
yes, but that is scientific network gain. I said.
Okay.
If you want to put it on the
Engineers are good.
electricity,
I'm not worried
yeah.
about the engineers. They come through when you need them. Okay, that's first. Second, when will we have rockets with humans in them that will use plasma propulsion? And will the first trip to Mars use it?
The first trip, I don't know, because it's possible that if all the resources are put there, you could get there once with chemical
Right.
propulsion. But again, to have a sustainable kind of travel, so you need plasma propulsion.
Does NASA have a group working on plasma propulsion? Or do they call you up to get their... What do we do next, Fatima?
Yes, give me more funding.
Yeah.
Yes.
Ah, there you go.
Oh.
I knew she'd be begging for money at some point. But how can a human travel that fast under? Isn't that an issue? Plasma propulsion? I mean,
It's a slow
it's
acceleration.
a slower acceleration.
Your face
Yes,
is
a
not going to do
slower-
this.
It's not.
you know.
No.
Not like, you know.
I wish I just wanted to get some of the lines out of my face. It seems like
Your
a
high
really
acceleration would get.
really fun way
you
to
get a
get some
little
plastic
facelift.
surgery.
Could I say that actually maybe we look at more closer, places to go, and I think moon could be, as I said, it could be just plasma propulsion. You don't.
What are we
need
going to do at the
fusion.
moon? We've been to the moon. What am I going to see at the moon?
Resources. There's all sorts
I got
of.
moon rocks in my top drawer of my drawer. Everybody.
No, you
Actually,
don't.
one of the way to actually create fusion energy, it's something is called aneutronic, means that you kind of you use deuterium, helium, to create energy, and you don't produce neutrons. So
That's just the PP chain in the center of the sun. There's no
Yeah.
loose neutrons
yes,
coming out of that.
Yes, exactly.
Right,
So it's
because neutrons are
aneutron.
bad because they
Yes.
come out and
Yeah.
nothing stops them.
Yeah.
Yes.
They don't have
yes.
a charge.
They're very pushy.
They're The advantage is they don't have to push. The other particles don't even know they're there. Am I right?
Yes,
With
yes,
neutrons?
yes,
It's
exactly.
like dark
yeah.
matter.
Neutrons, yeah. So that's a fun reaction in the sun. It's called the PP chain, the proton-proton chain. And it uses
Exactly.
deuterium and
Yeah.
tritium. No,
Yeah.
I don't remember tritium, but we have helium-3
Exactly,
is in there.
exactly. Helium-3, the so you have also fuel for also fusion. So there are things there, and you want to make some steps for the next generation, non-chemical propulsion. You first make some good step progress, and then gradually going further, you use fusion energy to go there. Yeah.
So in this process, you guys seem fairly lazy. You're taking your time, 5 years. Are you using, in all seriousness, how does AI factor into any of your work, or will it, in terms of the advancements you're trying to make?
It's a fantastic question. It's there.
Can you just say that again? Fantastic question.
I didn't hear it. I didn't hear her say that.
Fantastic. Yes.
Actually, she is AI right
Yeah.
here. She doesn't really exist. Did you think she was real?
I kept, and my finger goes right through.
It goes through her.
right through her leg. It's so
doing
weird.
a sound.
Yeah, exactly. I didn't want to say anything. I was like, I think she's been around the plasma too much.
She is plasma.
I'm sitting next to a plasmoid. Don't tell her.
Yeah. Yes, I think yes, definitely. Computers. First of all, most of the progress we made in plasma physics and fusion have always been, together. Experiments and advanced computation work together to make discoveries, and also any kind of achievement, it has to be together.
Well, I think we kind of need to wrap this
Yes,
up.
we do.
Yeah.
Yes, we do.
Unfortunately. This
Well,
is
Yes,
Fatima,
fascinating.
give me some words for the future.
Be patient in terms of...
Okay, we're fine. Okay,
Yeah.
I'm sorry I asked.
It's the answer's like this. Well, how do you define future?
Yeah. So let me say it. For the future is that progress and discovery doesn't happen overnight. It's the continuous work of scientists, long-term investments to kind of, you put all the energy you have, collaboration, all of that, and cross-pollination of various types of, group working on various types of plasma or types of devices, fusion experiments. Progress happened like that. So it's not. So it's also new physics. We learn every day in every regime of plasmas. We learn new things, and we apply it. Like this, rocket thruster. We apply it for other applications. What we learn in fusion, we also apply it for other applications. And so it's just
It's an ongoing process.
It's a continuous work.
So Fatima, typically at the end of our sessions, I offer the viewer a cosmic perspective on the topic of the day. But you so beautifully summarized the plight of the scientist, the engineer, society, funding sources. That's any and all that I would have said in my cosmic perspective.
Thank you.
So thanks for making my job just a little easier today. Good to have you, man.
Always great to be
All
here.
right.
Always learn a lot.
Fatima,
Thank you.
Good luck. You need some of that sometimes, right?
Yes.
When you're messing with plasma.
Yes, exactly.
And one day you'll give us a tour of your basement.
Exactly.
And listen, whatever you do.
Welcome, both of you.
Thank you. Well, and keep up your vague answers. No, it was really interesting. Very fascinating.
Thank you.
This has been StarTalk. Neil deGrasse Tyson here, your personal astrophysicist, reporting from my office at the Hayden Planetarium, the American Museum of Natural History in New York City. As always, keep looking up.